All right, guys, this is not how I wanted to present this to you here. With having a sick kid at home today on Monday, May 10th, just trying to get through it and do the best we can. I think that you can see that we're going to take a look at the last lesson here on the notes. And what we're going to do is we're going to basically learn a new log. Okay. So real quickly, we're familiar with this here. There are several different types of log. You might have log base 2. You might have a log base 7. You might just have the common log. Okay. The common log, if we recall, doesn't always have a number written after it, but the number that it always is 10, right? Well, there is one more type of log, okay? And we've seen this. This comes from the PERT formula, okay? But we've seen a log, and then this one is a base E. So that's what I mean about the PERT formula. This base E right here is essentially a way to come up with what is called a natural log. So we've done actually a lot of things with interest formulas and things like that. Sorry, I was checking to see if my audio was on here. The natural log is a way that things progress or maybe deteriorate in real life. So I know we've talked a lot about animal populations or populations of humans. You say like, hey, there's 20 people, it increases at 7%. How much money or how much people would be there, after 5 years? Well, really the best formula to use for that is the compounded continuously formula. I'm not really concerned about that for this year, but when you get to college algebra, pre-calculus, that's really what they're going to focus on more. So we want to go about this idea of having this log base E. Now, we won't see it written this way. What we're going to do is we're going to see it written this way. This stands for the natural log. Okay. Now, this symbol right here always has a base E. Okay. Always a base E. Okay. Just like if I didn't see a number, it was always 10. This one is always a base E. So you'll never see something like this. Okay. That will never happen. Now, it sounds backwards. Okay. But it's read as the natural log, right? So that's a lowercase l, lowercase n. All right. This is probably one of the most applicable logs in real life for that. So to get that straight, these two can be written back and forth. So I know that, just kind of a quick review, that if I had a raised to the b equals c, that was the same as log base a of c equals b. Okay. But when I have a e raised to the a equals b, that's the same as the natural log of b equals a. Let's kind of explore this a little bit more here. One thing that we know, and again, I'm just using A's and B's, and in this case, C's, just to represent numbers. E is an actual number, if you remember that in the calculator. Whatever was the exponent is always the answer. And that's the same thing here. Whatever the exponent, E raised to whatever power, is the answer in log form. Whatever is the answer goes as the argument here. Again, you don't need to write this, but there is an understood E right there, okay? These natural logs, they have the same exact properties as the log logs. You can condense them. You can use the product property, the quotient property, the power property with it, all right? And so we're gonna actually take a look at practicing that right here. So if we look at A, we could say, I got 2 times the natural log of 15 minus the natural log of 75. So when we're looking at this right here, we note that the 2 is really in front of the natural log. So it really goes right here at the end. So the natural log of 225 minus the natural log of 75. Now with that minus sign, we know to divide. So the natural log of 225 over 75. Let's see here. That's going to be, what is that going to be? 9 over 3 or just 3, I guess, the natural log of 3. Now, I could put this in the calculator, and maybe you want to do that, but it's going to come up with a random decimal. Okay, so recall that for these log logs, you could only put it in the calculator for when it was a base 10, but these natural logs, you can always use the calculator. Now, I don't need to do that right here. There's no reason to express this as a random decimal, but just know that I can always take the natural log of these numbers in the calculator, right? And so that's one nice thing. Again, basically what that means is e to what power equals 3, okay? If I was going to say, e is the base of the log, and then obviously we don't have an answer, so e to what power is 3. That's what it would be saying there in the calculator. We could keep going here, right? For letter B, natural log of 7 plus 2 times the natural log of 5. So the natural log of 7 plus the natural log of 5 squared. We know that's just going to be 25. So the natural log of 7 plus the natural log of 25. Now we know to multiply those, and we just have the natural log of 175. Again, we could put that in the calculator. Not really a need to, just because we would just get a random decimal with that. One interesting thing here is that one thing with these is that sometimes you can come up with, and you can actually use these natural logs for the change of base. So if I had log base 3 of 5, I know that I could put this in the calculator here. I actually get the same answer. These are the exact same if I take the natural log of 5 over the natural log of 3. This works because the bases are the same on the top and the bottom. Bases were 10 here, log base 10 of 5, log base 10 of 3. This is a log base E of 5 and a log base E of 3. So we can really use the natural log for this change of base formula. All right. So let's try a couple more here. These last ones are maybe a little bit more intense, but let's just see here. We know that we have things that are going to be with the exponent. So it's going to be the natural log of x squared minus the natural log of 2x squared. Notice that the 2x, they're both with this natural log right here. So therefore, they both need to get squared. So the natural log of x squared, I'm just going to simplify this here at the end. We know that we can just now divide with the x squared on top and the 4x squared on bottom. It looks like we have some reducing. We have a common factor of x squared on top and bottom. So the natural log of 1/4 there. That's what the simplification process would be here. One last one's really trying to hit heavy with these exponents with this 3 and the 2. Natural log of x cubed plus natural log of y squared plus the natural log of 5. Because they're all positive natural logs, they all go on top of the fraction, unlike here. We had a negative natural log, so again, they went to the bottom of the fraction. So we could simplify this, and usually we write the coefficient or the number in front, followed by just an alphabetical order. All right. Now, here's where we come up with actually solving some of these problems here. All right. So when we're looking at this, in example 2, solving an exponential equation, we have it written as such. So we're actually going to use these same rules that we talked about on Wednesday or Thursday, depending on what day your class is here, right? So solving this equation, we're just going to isolate the base and the exponent here. So we're going to do everything we can to get this e raised to the 2x by itself. So again, I really have a 4, and then I have something that I want to isolate. Plus 2 equals 16. I'm writing it this way to help us think, would I divide by 4 first or subtract 2? It really doesn't matter, but there is a way to do it probably more commonly without fractions. I would subtract 2, and that would equal 14. I would divide by 4, and that would equal 7/2 or 3.5. And now what I have here is that e raised to the 2x equals 7/2. Now, basically what I've done here is just step 1. Okay. So what I'm going to do is I'm going to just kind of move this over here. It was e raised to the 2x equals 7/2. Now notice what I'm going to do here. I can't put this into the calculator, okay? I don't have my actual calculator here as far as the one that I usually use in class. So notice that when I look at a calculator here, again, ideally we're not using a cell phone here, but I have my e raised to the x button. Okay, let's see if we can make that a little more clear. Not really. I have my e raised to the x button right here. And I can't find it because it says 2x right here, right? 2x. I don't really have an x button on here. So I can't just plug that, in this case, red part of the equation in my calculator. So what I'm going to do here is I'm going to write it in logarithmic form. I'm going to rewrite it in log form. So e raised to the a was b. That can be interchanged with, let's see if I can make this a different color just so it kind of pops out and we know it's not part of that. E raised to the a, or e raised to the a equals b. It's the same as the natural log of b equals a. Remember, the exponent is my answer. So I have the natural log of 7/2 equals my 2x right here. Now I have something that I can put into the calculator. So where this natural log button is in your calculator, the natural log button is very close to your e button. All right. So if you know when you would use the PERT formula, e raised to the x, in this case, there's my e raised to the x, and just below it is my natural log. So in most cases, you have to hit the natural log first, but because of the calculator I'm using, I need to hit the natural log second. So basically what that means is e to what power is 7 over 2 or 3.5? It's 1.2567. Right? So I'm going to leave this so far just written down this way, the natural log of 7/2. And again, in order to get x by itself, I'm just going to need to divide this whole thing by 2. So we talked about in the past that this right here would be my exact answer. Right? But sometimes it also asks for an approximation. So here's what I have in green. Then I just need to divide it by, it looks like 2. So my answer, or my approximate here, is just 0.626. Okay, again, we could check that out. We have 4 times e raised to the 2x. So in this calculator, I kind of have to do it backwards. I'm going to say, here is my number. It's 0.626. I'm going to take it times 2. Whoops, it's out of the frame there. Times 2, because that's both in the exponent. I'm going to raise it to e. I need to take it times 4 plus 2, and it's 15.989. There it is, 16. All right. So we're just kind of going through these numbers. I could use change the base, but again, I really can just plug this into the calculator, so it's not really that big of a deal. The logarithmic one is the same way, okay? What I mean by that is, and we'll take a look at least one of them here. Let's see here. We'll take a look at this. We'll change out this problem right here. So let's kind of keep going with this, all right? It looks like E and its exponent is already isolated. So step 1 is already done for us. Step 1 is already done for us. So that's going to look like the natural log of 12 is going to equal x minus 2. I know in order to get x by itself, it's going to have to say plus 2 on the other side. Now remember, notice that the 2 does not have a natural log with it. I don't multiply these numbers, right? I don't need to multiply these numbers here. Let's see if I can come up with a random sheet of paper here. If it said the natural log of 12 plus the natural log of 2, then I would multiply them, but there's no natural log there. Okay. So again, if you really need to, we can have the natural log here. So I'm going to have 12, and then I'm going to have the natural log button. And then it's just going to be plus 2. Okay. So here is my exact answer. And then my approximate is just 4.485. All right, for that approximate answer. All right, let's try 2 more here. One more that starts with an E, and then we'll get to one that's a natural log. Again, we have the steps for the logs, and it's really no different, okay, from before. Let's take a look here. It doesn't look like this E is by itself. So 2 times something, and that's what I want to get by itself, equals 20. So that something equals 10, 2 times that missing number. So I'm going to divide by 2 to get 10. So E raised to the opposite of X is the same as 10. Notice I can just rewrite it in natural log form. Notice that E is not there anymore because now it's right there with the natural log. So one thing that you could do here is we know that we're going to be dividing. So this negative sign is going to be with the natural log. And that right there is going to give us our exact answer. And now we can go ahead and plug it in. Again, if you need to, you can just plug it in as you go through this process, right? So let's see if we can get this kind of flipped around here. There's the calculator I need. All right, so we have, what was it? The natural log of 10. So 10 with the natural log. And then I just needed to take the opposite of it, right? So divide it by a 1 that's negative. Just the same number as before, but just the opposite. So negative 2.303. Again, that's just my approximate value right here. Okay. I will put these up on OneNote here after we finish this last problem. So let's take a look at it here. Again, I said I was going to switch it around. One reason for the switch is because I want us just to be able to see what the natural log does. So we'll keep it short and simple. We'll say the natural log. Oops, I messed that up. I put like an H instead of an L or an N. The natural log of 4x equals 17. The natural log of 4x equals 17. So it looks like the log is already, let me move this over here. Looks like the log is already isolated or condensed, right? Nothing on the outside of that. So I'm going to say that it's going to be an e to the 17th power equals 4x. Now I can do this here. So it looks like e raised to the 17th, divide it by 4. And we know that it just equals x. That would be my exact answer right here. Now we can use the calculator. Be prepared for this to be a ginormous number. When I wrote it just after I did, I said, ooh, I'm going to have e to the 17th power. That could be a little bit bigger than I was anticipating. So here we go, 17, and then e, look at that. That's over 24 million right here. I know I'm going to divide it by 4, which will decrease it, but not by a lot, just over 6 million. So here we go. We have 6,038,738.188 there. That is my approximate value. Now, this is kind of an interesting thing. If we did check it, again, we could say 4 times 6,038,738.188 equals, because I multiplied it by 4, just plugging it back into the original. I could then take the natural log of that and see how close my answer is to 17. Again, basically e to what power is that 24 million? Well, the reason it was 24 million is because I had to multiply by 4. So e to the 17th power was that 24 million. All right, guys, we're going to take a look a little bit more at this. Do not forget, we're planning for a test on Friday for e-learning. So I planned here to be back on Wednesday so we can connect then. Just having a review assignment, nothing in particular, but this assignment will be open for full credit throughout this entire week. All right. Please let me know if you guys have any kind of questions. I'll do my best to monitor the email, but there is going to be a Math Excel assignment, and you can see that on Canvas. All right, guys. Thank you.